Welcome back to the deep dive. We have a rather substantial document on the desk today, one that really forces us to take a step back from the daily news cycle and look at the structural machinery that's working underneath it all. We're going to be dissecting an essay. It's titled The Weight of Progress by Lev Neymotin, PhD.
It is a heavy text, for sure, both in its
Yeah.
subject matter and, in its implications.
It is. And this piece, it's part of Neymotin's Uncompressed Thinking series, which you can find on YouTube. And I want to pause on that title for a second, Uncompressed Thinking.
Right.
It kind of suggests that we're usually operating in a compressed state, doesn't it? That we're always trading nuance for speed.
That's exactly the premise. I mean, we live in an era of headlines, tweets, executive summaries. Neymotin is an engineer by training, and his Uncompressed series is really an attempt to, unpack the full file, so to speak. He's looking at these really complex systems without trying to dumb them down for a mass audience. He wants to understand the physics of how systems grow, how they succeed, and then ultimately why they tend to get so heavy that they stop functioning.
The central metaphor here is weight. But before we get to that, we should probably establish the lens he's using. You said he's an engineer. How does an engineer's lens differ from, say, a historian's or an economist's when you're looking at something like progress?
It's a really distinct shift in perspective. A historian, they might look at the narrative, the story of a civilization or a technology.
Sure.
An economist would look at the flow of capital or value. But an engineer looks at a system as a machine that consumes energy to perform work. And because of that, the engineer has a professional obligation, really, to ask a very uncomfortable question.
Which is?
Does the system still pay rent?
Pay rent. Okay, that sounds financial, but I'm guessing he means something more fundamental than that.
He does, yeah. He's talking about thermodynamics and utility. Every single system, whether it's a biological organism, a corporation, a scientific field, it consumes resources.
Right, time, energy, people.
Energy, time, talent, exactly. So to pay rent just means that the output of that system, the problem it solves, the value it creates, it has to justify that consumption.
So it's a ratio.
It's a ratio, an input-output ratio. And the core argument of this entire essay is that this ratio, it's not static. It changes over the life of a system.
Okay.
And there's this recurring pattern where success produces growth, growth produces weight, and then eventually that weight undermines the very usefulness that started the whole process in the first place.
So let's walk through that trajectory because he breaks it down into distinct phases. It starts with what he calls phase 1, generous returns.
This is the golden era, the startup phase, if you will,
Yeah.
but it applies to civilizations too. In this phase, you make a tiny investment and you get a massive return.
Can you give an example?
Sure. Think about the transition from a hunter-gatherer tribe to the first agricultural city. Or a better one, maybe, the invention of the optical microscope.
Right. You grind a piece of glass, which is pretty cheap, and all of a sudden you can see this entire hidden universe of bacteria.
Precisely. The input is incredibly low, a piece of glass, a frame, but the output is a complete revolution in medicine and biology. Progress in this phase feels light. It feels almost effortless.
The wind is at your back.
Exactly. You build a simple tool, and it solves a massive, screaming problem. The rent is easily paid. There's no question about it.
But systems don't stay there, do they? We don't just build the microscope and then stop. We want to do more.
We do. And to do more, we have to organize. And this leads to phase 2, which he calls structure and overhead. To scale that initial success, you need structure.
Okay.
If you want to distribute microscopes to every hospital in the world, you suddenly need a factory. You need managers. You need supply chains.
Well, structure seems necessary. I mean, you can't have impact at scale without it, right?
You can't. And that's the trap. It's a necessary trap. Structure enables scale, but it always introduces overhead. Suddenly, you aren't just grinding lenses anymore. You're managing HR disputes. You're fixing conveyor belts. You are filing taxes. At first, we accept this. We say, well, okay, overhead is just the price of sophistication. And for a while it is. The system is still paying its rent. But the profit margin, let's say, is getting thinner.
And that slides into phase 3.
That slides right into phase 3, self-reinforcement. And this is where the engineer, the one asking about the rent, starts to get really worried.
Why?
Because the system has become so large and so complex that it devotes the majority of its energy just to maintaining itself. It's no longer primarily focused on the mission. It's focused on its own survival.
Is this what he means by weight? The overhead?
Yes, that's the weight. The usefulness plateaus, but the complexity just keeps rising. The system starts creating work for itself. The bureaucracy generates regulations that require more bureaucracy to interpret and enforce. The machine just gets heavier and heavier, not because the problem requires it, but because the machine is designed to grow.
He has a definition for collapse in this context, and it really wasn't what I expected. When we hear collapse, we think of something sudden, a catastrophe.
The Roman Empire burning.
Yeah, or the stock market crashing to zero in a day, a big event.
Right, we expect a Hollywood explosion. But Moten's definition of collapse is slow, expensive, and internally rationalized.
So it doesn't explode, it just calcifies.
It calcifies. It becomes incredibly expensive to operate, but it produces very little new value. It just sort of grinds on.
There's a line in the text that really stuck with me. He says, "The system exists because it already exists."
That's it. That is the circular justification of what you could call a zombie system. It loses the connection to its original purpose, solving a problem, and it simply continues because the momentum of its own existence is too great to stop.
Okay, so to illustrate this, the essay takes us into two big case studies. And the first one is, it's quite bold. He targets a field we usually consider the pinnacle of human achievement, high-energy physics.
It is a bold choice, absolutely. He dedicates the whole first part to high-energy physics and the end of the generous curve. Now, we have to be clear, and he is very clear about this in the text, this is not an attack on science.
No, of course not.
He fully acknowledges the monumental triumph of the field.
It's a standard model.
The Standard Model, which is arguably the most successful theory human beings have ever constructed. It explains the fundamental building blocks of the universe with just incredible precision. I mean, we went from classical mechanics in the 19th century to quantum field theory in the 20th. That journey was just a series of generous returns, one after another.
And the discovery of the Higgs boson a few years back.
That was the crowning achievement. But Moten argues that the Higgs boson was the closing of a loop, not the opening of a new frontier.
What's the distinction?
It confirmed a theory that had been proposed decades earlier. It was the final, missing piece of the puzzle. We already had the picture, we just needed to find that last piece to prove it was correct.
But isn't that a success? Finding it.
Oh, it is a success. A huge success of verification. But look at the cost. To find that one particle, we had to build the Large Hadron Collider, the LHC. This is a machine the size of a city, costing billions of dollars, requiring thousands of the world's smartest people and just immense amounts of energy.
And now there's talk of the next one, the Future Circular Collider, the SCC.
The FCC, a proposed 100-kilometer tunnel. This is a project on the scale of national infrastructure, like building a new highway system. And this is where that engineer's lens really kicks in. Moten points out a fundamental shift in the methodology.
Okay.
In the generous returns phase of physics, insight preceded scale.
Meaning the idea came first.
Meaning a physicist would have a specific question, a paradox in the math, or a gap in the theory. They would then build an instrument specifically designed to test that idea. The machine was a servant to the insight. The instrument was built to answer a question.
And now?
Now, the relationship is inverted. We don't really have a screaming paradox telling us exactly where to look next. The Standard Model works almost too well. So the strategy is shifted to scale first.
Right.
We build a bigger machine, push to higher energies, smash particles together with more violence, and we just hope that something new and unexpected appears in the debris.
So we're building the machine not to test a specific prediction, but more to see if there's anything left to find at all.
Exactly. Scale is being used as a substitute for direction. And the cost of that exploration is astronomical. And this leads him to introduce the concept of conceptual return per unit of energy and complexity.
That's the rent.
That is the rent. In the 1920s, a small lab with a couple of people could revolutionize our entire understanding of reality. The return on investment, on energy, was huge. Today, we are proposing a 100-kilometer tunnel to measure the properties of particles we already know exist, with just slightly more precision. The return per dollar, per watt, per career spent has just plummeted.
It sounds like he's describing a classic point of diminishing returns.
It is the textbook definition of diminishing returns. And he poses a very difficult question. Is the discipline extending our understanding of the universe, or is it merely extending itself? Is it building the next bigger collider? Because that's what physicists do.
That's that circular justification again. We build colliders because we are collider builders.
And his conclusion on physics is pretty sobering. He suggests it hasn't failed, not at all, but that it has reached the natural end of its most productive phase. The universe, it's not obligated to provide us with new, easy-to-find physics just because we build a bigger machine.
Right.
We might just be entering what he calls a desert, a vast range of energy where simply nothing new or interesting happens.
So if there is more insight to be had, it might not come from brute force.
It might require a conceptual reorientation, a new way of thinking, a new theory, not just a bigger hammer.
Which brings us to the second case study. So if physics is the old, heavy system, part 2 introduces the new, exploding system, artificial intelligence.
The return of the furnace, as he calls it.
This feels like a contradiction at first. Physics is mature, maybe even plateauing. AI is brand new, it's culturally dominant, and it's moving at breakneck speed. So how can they possibly be subject to the same problem?
And this is why the structural analysis is so interesting, because on the surface, you're right, they look like polar opposites. But underneath, Nemotin argues, AI is mirroring the exact same structural flaws as late-stage physics. It is relying on brute force scaling.
You mean the bigger is better approach? More data, more compute?
Exactly. How are we achieving these incredible leaps in AI performance? Are we discovering fundamentally new paradigms of intelligence? For the most part, no. We're taking the same basic architecture, the transformer, and we're just scaling it up. More layers, more parameters, more training data, and crucially, more computation.
So much more computation.
You're just shoveling more coal into the engine.
We are. And this brings us to the energy problem. We often talk about AI in these abstract terms like safety or jobs or copyright. But Nemotin wants to ground us in the physical reality of it. AI is infrastructure. It is data centers.
I've seen some of the reports about data centers consuming the power of entire small nations.
It's becoming a serious, serious issue. They draw immense amounts of power. They require massive water cooling systems. They occupy huge tracts of land. In some regions, the demand from new data centers is actually competing with the residential power grid.
Wow.
But the most damning point Nemotin makes is the comparison between AI and the biological standard.
The human brain. The human brain. Just consider what your brain is doing right now. You're listening to me, you're processing complex language, maintaining your posture, regulating your heartbeat. Maybe you're thinking about what you're having for lunch, and you're synthesizing all of this with your memories.
And I'm doing all of that on, what's the number?
It's about 20 watts.
20 watts, like a dim light bulb.
A very dim light bulb. The efficiency is just staggering. The brain is an incredibly elegant machine. It learns continuously, it adapts to context, and it operates on a caloric budget that would barely power a laptop fan.
And the AI to do similar tasks.
To replicate even a narrow slice of that capability, say generating text or recognizing images, we are building clusters of GPUs that consume megawatts.
Megawatt.
We are using orders and orders of magnitude more energy to achieve a result that biology achieved with, a sandwich.
But wait, I have to play devil's advocate for a second here. Isn't this just a temporary problem? We always hear about Moore's law. Chips get smaller, they get faster, more efficient. Won't the hardware eventually catch up and just solve this energy problem for us?
Right. The technology will save us. Nemotin addresses this directly. He calls it the hardware myth. And it's a dangerous assumption to believe that hardware improvements will infinitely bail us out of an inefficient design.
Why? I mean, hasn't it worked for the last 50 years?
It has, but we're hitting hard physical limits. You can only shrink a transistor so much before quantum effects start to interfere and things get weird. We're seeing a slowdown in what's called Dennard scaling. And then there's the thermal limit, just raw heat. You can't pack chips any denser without them literally melting.
So we can't just shrink our way out of this problem.
And even if we could, let's say chips got twice as efficient next year. What does history tell us we would do with that extra efficiency?
Build bigger models.
Jevons paradox.
Yeah.
We wouldn't save energy. We'd just build models that are 4 times bigger.
Yeah.
The demand for compute and AI is growing far faster than the efficiency of the hardware is improving.
What about quantum computing? Is that the magic bullet that everyone talks about?
He kind of dismisses it as a speculative alternative. It's a maybe, a big maybe. But there's no guarantee that quantum architectures are suitable for general-purpose intelligence or that they'd be more energy efficient for these tasks. So, relying on a hypothetical future technology to solve a fundamental physics problem in your current design is, well, it's risky.
So AI is falling into that same trap of self-reinforcement, too.
Yes. Power substitutes for understanding. As long as we can pour more energy into the system and get a marginally better chatbot, we rationalize the enormous cost. We say, look, it's working. Keep building.
Right.
But we're avoiding the much harder question, which is this architecture actually efficient? Or are we just force-feeding it with so much power that it can't help but work.
And the prediction then is that AI will eventually hit the same wall that physics has hit.
The question will come, what if the next leap in capability cannot be purchased with more energy? What happens when you build a data center the size of a city, and the model doesn't become sentient? It just becomes a slightly better parrot.
That's the wall.
That's the wall. And when you can't buy progress with scale anymore, you have to go back to insight. You have to find a better idea.
This seems to bring us to the very center of the essay. We've looked at physics, we've looked at AI, but now Nemotin zooms out to show us what he calls the universal sequence. This is the pattern that connects everything.
This is really the theoretical skeleton of the whole piece. He outlines this 5-step pattern that he sees everywhere.
Okay.
1. A system emerges to solve a problem. 2. Success encourages growth. 3. Growth produces complexity. 4. Complexity produces dependence. And 5. Dependence produces weight.
Step 4, dependence. That's the one that feels the most insidious to me.
It is, because we become dependent on the complexity we've created. We forget how to solve the original problem without the massive apparatus we built around it. And that leads to this critical distinction he makes between productive growth and defensive growth.
Could you unpack those terms for us? What does defensive growth actually look like in practice?
Sure. Productive growth is easy to spot. You add a resource, you get a new capability, you hire a scientist, you get a new discovery, you build a factory, you get more cars, the output increases. Defensive growth is when the system expands just to preserve the conditions that allow it to operate.
So basically maintenance.
Maintenance, but it's like aggressive maintenance. You hire a team of lawyers to defend the patent that allows your factory to run. You hire a compliance officer to manage the regulations that the previous compliance officer wrote.
Right.
Nemotin calls this maintenance growth. And from the inside, it feels like responsible management. You're mitigating risk, you're being prudent. But in reality, you're consuming more and more resources just to remain what you already are.
You're running faster and faster just to stand still?
That's it, exactly. And he gives us the 3 replacements to help diagnose this in any system. If you want to know if your system, your company, your project is getting heavy, look for these 3 signs.
Okay, let's go through them.
The first one is scaling replaces insight. When you run out of clever ideas, you just make the existing idea bigger.
Just add more.
The second is energy replaces efficiency. When you can't design a more elegant solution, you just overpower the problem with raw energy or money or brute force.
And the third?
The third is administration replaces adaptability. When the coordination costs get too high, instead of simplifying, you just add more layers of management. You replace the ability to pivot quickly with the ability to fill out forms correctly.
Administration replaces adaptability. I mean, I feel like we see that in every large institution, from government to corporate conglomerates.
It's the universal sign of aging in the system. And Nemotin's verdict here is very precise. He doesn't say the bureaucracy is evil or bad. He says it becomes disproportionate to purpose.
Okay.
The collapse happens when the cost of all that administration exceeds the value of the coordination it's supposed to provide.
There's another great line here. Collapse is a correction imposed by constraints that were postponed.
That's the one. We postpone the constraint of efficiency by burning more energy. We postpone the constraint of insight by building bigger machines. But eventually, the bill comes due. The postponed constraints reassert themselves.
Okay, moving on to part 3. This is where the essay gets really big picture. Biological and civilizational parallels. He's arguing this isn't just a technology problem, it's a life problem. It's built into the universe.
This section puts our current struggles into, deep time. He looks at biology, and specifically at this tension between optimization and flexibility.
He uses the dinosaur example. Now, usually dinosaurs are sort of the punchline for failure, going the way of the dinosaur. But he frames them very differently.
He does. He argues that dinosaurs weren't failures at all. They were victims of their own stunning success. They were highly, highly optimized. To be a dominant species in the Cretaceous period, you had to be big. You had to specialize.
And specialization is very efficient, as long as the environment is stable.
It's exactly. If the environment is stable, lots of food, warm weather, then being a massive specialized eating machine is a fantastic strategy. You outcompete everything else. You optimize for dominance. But that optimization comes at a cost.
Flexibility.
Flexibility.
Because you're so perfectly adapted to this specific world, you can't live in that specific world when things change.
That's it perfectly.
Right.
When the asteroid hits, or even more simply, when the climate just shifts rapidly, that high degree of optimization becomes a massive liability. The dinosaur is heavy. It has huge metabolic demands. It cannot pivot. The small, scrappy mammal, on the other hand, is inefficient by comparison. It's not dominating the food chain, but it is flexible. It can eat almost anything. It can hide in a hole. It has lighter requirements to survive.
So the concept is success-induced fragility. You become fragile because you were so successful at adapting to the old world.
Yes, and he applies the same logic to civilizations.
How does that map onto human history?
Well, think about the trajectory of empires. Early expansion solves coordination problems. We come together, we build irrigation systems, we build walls to protect our grain. This is productive growth.
Right.
But over time, the administrative complexity grows. We need a standing army to protect the walls. We need tax collectors to pay the army. We need scribes to watch the tax collectors.
The overhead grows and grows.
The overhead starts to eat the surplus.
Yeah.
And as long as conditions are stable, the weight is bearable. The society can afford its own bureaucracy. But when conditions change, a multi-year drought, a new plague, a shift in trade routes, the cost of maintenance suddenly exceeds the benefits.
And that is the collapse.
That is the collapse. Yeah. It's not just barbarians at the gate. It's that the society has become too expensive to maintain relative to what it produces. There's a mismatch between its scale and its adaptability. The system is too heavy to move, but the world is moving all around it.
So the unifying theme here isn't failure, not really. It's overextension.
Overextension. Systems struggle to remain aligned with the conditions that once justified their scale.
This brings us to the conclusion of the essay, choosing lighter futures. I like that he circles back to that word weight. He clarifies that weight isn't inherently a negative thing.
No, not at all. Weight is often the accumulation of achievement. A library is heavy with knowledge. A city is heavy with culture and infrastructure. We should be proud of what we've built. But weight requires support, and support requires justification. The problem arises when we start to confuse motion with direction.
Confusing motion with direction, that feels like the defining characteristic of modern work sometimes.
It is. We start to protect the system itself rather than serving the purpose the system was created for. We equate seriousness with cost and scale. We think, well, if this project cost $1 billion, it must be important. If this meeting has 20 people in it, it must be serious.
Instead of asking if it actually provides any clarity or insight.
Exactly. We start to value the complexity of the machine more than the output of the machine.
So what is the pivot point? What do we do about this?
For physics, he suggests the field needs to accept that the era of big iron, of simply building larger and larger colliders, might be over for now. The path forward is probably conceptual. We need a new Einstein, not a new tunnel. We need to rethink the theory, not just stress test the old one with more and more energy.
And for AI?
For AI, we need to stop trying to brute force intelligence. We need to look at that 20-watt brain and ask, how is it doing that? We need to prioritize efficiency as a primary design constraint, not as an afterthought we hope hardware will fix later. If we want intelligence that can actually be integrated into the world without, burning it down, it has to be lighter.
And for us, for the listeners, the individuals in their own lives and work.
For us, I think it comes down to what he calls mature ambition.
How does mature ambition differ from regular ambition?
Well, regular ambition is usually defined as endless expansion. More revenue, more headcount, a bigger house, more followers, just more. Mature ambition recognizes that true progress is about the alignment between your means and your ends. It constantly asks the question, is this growth actually serving the purpose?
And if it's not,
then you have to be willing to subtract, to simplify. When that alignment is lost, a collapse or just scaling back, it's not a tragedy, it's a correction.
A correction, that's a very different way to frame it. So instead of fearing the downsizing or the simplification, you can view it as the system getting healthy again.
Exactly. The challenge isn't always how to add more weight. Sometimes the real challenge is how to recognize when progress must become lighter.
That is a profound place to land. It really forces you to look at your own projects, your own company, maybe even just your own habits and routines.
It does. We are all building systems in one way or another. And the laws of physics, the laws of thermodynamics, they apply to all of them.
So as we wrap up this deep dive into Lev Motin's The Weight of Progress, I'm left with that engineer's question just ringing in my ears.
That's a question we should probably all ask ourselves more often.
Is your system paying rent? Is the weight you're carrying justified by the value you're creating? Or are you just growing because you're already there?
It's definitely worth thinking about.
Thank you for listening to this episode of The Deep Dive. If you want to explore the source material for yourself, check out the Uncompressed Thinking channel. It's worth the time. We'll see you in the next one.